today we will first try to see a proof of this proposition which I wrote down last time. Recall the proposition that we are concerned about quadratic surface. Quadratic surface is defined as S in R3 is called quadratic if it is the form R dot A plus B dot R plus some constant C, where R is a vector x y z, A is a 3 cos 3 symmetric matrix and B is a fixed vector constant vector in R3 and C is a constant in R. And A we have taken let me write it again. We will take A just to for our calculations, we will take A in this form. So, 3 cos 6 symmetric matrix So, I will put the diagonal entries as A1, A2, A3 and off diagonal entries A4 here. If I put A4 here, then I have to put A4 here. I put A5 here, I have to put A5 here, A6, A6. That makes a symmetric matrix, right. So, this is just for convenience I write it in this way, because in the proof we will be manipulating with these numbers. So, such a thing is a quadratic surface, and if I expand this in terms of this matrix A, R and B and C, then I get a equation like this. And we have noted that it may not be always a surface, because in particular cases when A1 equal to 0, A3 equal to 0, other constants are 0, sorry, A1, A2, A3 are 1 and other constants are 0, this becomes x square plus y square plus j square equal to 0, this becomes origin. Similarly, it can be a circle, it can be pair of straight line. So, accordingly we wrote down this proposition. Just read it again, that by applying a rigid motion in R3, every quadratic surface in which all the coefficients are not all 0. So, I am not looking at the equation 0 equal to 0, can be transformed into a surface with Cartesian equation one of the following, where P Q are non-zero constant. First of all, it can be an ellipsoid. Second, so possibilities, there are 10 possibilities, right. I wrote down somewhere, sorry, 14 possibilities are there, and I listed down all the possibilities: ellipsoid, hyperboloid of one sheet, hyperboloid of two sheets, elliptic paraboloid, and equations are written accordingly. Hyperbolic paraboloid, this is fifth one. Sixth is quadratic one, a quadratic cone. Seventh is elliptic cylinder, hyperbolic cylinder, parabolic cylinder, this one. It can be a plane, two parallel planes, two intersecting planes, straight line, a pair of straight line. Now, this is just a straight line, x square plus y square. So, this is straight line or a single point. So, in that case, in last two cases they are not surfaces in R3. So, how does one prove this? As I said, this all depends on this. Since I have a symmetric matrix A, let me write down A again, A1, A2, A3, A4 here, so A4 here, A5 here, so A5 here, A 6 here, so A 6 here. Now, all you know, if I have a symmetric matrix, 3 cross 3 symmetric matrix, then my knowledge of linear algebra tells me that there exists a orthogonal matrix actually. There exists a matrix P such that P transpose P is identity, also determinant P is 1, and P transpose A P is a diagonal matrix. Right. So, let this diagonal matrix D be A1 prime, A2 prime, A3 prime, rest entries are 0. So, any 3 cross 6 symmetric matrix is diagonalizable with real entries. I mean, these eigenvalues are real, these are eigenvalues, right. A1 prime, A2 prime, A3 primes are eigenvalues of A, and corresponding columns of P transpose are the eigen vectors of A. Corresponding columns of P transpose or rows of P, they are eigen vectors of A. So, what we do? We make a transformation that our R was x, y, z. What I do? I put x prime, y prime, z prime correspondingly as x, y, z, this row vector P. This is a row vector again. Similarly, our B was, we have taken B1, B2, B3. So, I take, so let us put it R prime. Similarly, I put B prime, B1 prime, B2 prime, B3 prime is equal to maybe I put the vector sign also. So, what will happen to the original equation? What was the original equation? R dot A plus B dot R plus C equal to 0, right. So, if I multiply P transpose on this size and P, so I put a P transpose P and P transpose, so C does not matter. So, this is identity, C remains C because P transpose P is identity, C is a constant, but this fellow is identity, this is 0. Now, what will happen according to these equations? This will become now R prime D R prime plus B prime R prime plus C, and now D is this matrix. So, this becomes A1 prime x prime square plus A2 prime y prime square, A3 prime z prime square plus B1 prime x1 prime, B2 prime x2 prime plus B3 prime z3 prime, sorry, x3 prime plus C equal to 0. So, this equation I have reduced into this, but in reduction what I have done? I have applied some rigid motion in R3, because multiplying with a orthogonal matrix, P is orthogonal, P transpose is orthogonal, multiplying in orthogonal matrix will give you a rotation around 0. So, that is a rigid motion of R3. So, by a rigid motion, that is a rotation around origin, I have reduced the original equation of the quadratic surface to this one. So, let me now get rid of this prime and we will assume that our surface is, our quadratic is a1 x square plus a2 y square a3 z square plus b1 x, just for avoiding this writing prime every time, b2 y plus b3 z plus c equal to 0. So, I have not done nothing, I have just written this equation instead of x1 prime, this instead of prime I have just get rid of prime and we will assume that our equation is in this form. So, let us call this a star. Now, observe how do I deduce all the cases. Suppose a1 is not equal to 0, then the idea is I will get rid of b1. How? Define x prime equal to x plus b1 by 2 a1, which is a translation, right. Then I can write this equation, star becomes, you put x equal to x prime minus this, so x square there. So, what will happen? The star becomes a1 x prime square plus a2 y square, these are not touched, z3 square, sorry, z square plus b2y, b3y, b3z is not touched, this constant will change because there is something here, some c prime equal to 0. Try that, this will just put, instead of x you put x prime minus b1 minus 2 a1. So, this b1 x term will go out, correct, because 2 x1 b1 divided by 2 a1 will coming, a1 will cancel that and this negative, that will cancel b1 x. So, we can assume b1 is 0. If a1 equal to not equal to 0, we may assume b1 is 0, because b1 is not there, I can get rid of it by a translation. Similarly, for if a2 is not equal to 0, I can get rid of b2, a3 is not equal to 0, I can get rid of b3. So, and so if a1, a2, a3 are all non-zero, then by tree translation I need exactly 3 translation, we may assume star is of the form a1 x square, a2 y square plus a3 z square plus some constant equal to 0, call it double star. Right. So, if C not equal to 0, what happens? Let us go back. C not equal, so this is my, after rotation and translation, my surface becomes this, C not equal to 0. Then you see, depending on the sign, I can normalize. So, depending on the sign of A1, A2, A3, I will get case 1, case 2, case 3. I will divide by C minus C, I will get 1 here, 1 on the right hand side, and depending on this case. So, what I mean here, that now you take this C right hand side. So, this is actually minus A1 by C1, sorry, C x square plus minus A2 C y square minus A3 by C z square equal to 1. So, this is my, these are my 1 by p square, 1 by q square, 1 by r square. So, depending on sign of A1, A2, A3, I will get either ellipsoid, hyperboloid of one sheet or hyperboloid of two sheets, correct. What happens C equal to 0? You can see from now, if C equal to 0, so C not equal to 0, I get case 1 or 2 or 3. If C equal to 0, then we will get 4 elliptic paraboloid, C equal to 0, sorry, not 4, 6, right, yeah, this one, either 6 or there is another one, that is or this one, 14. C equal to 0, so this is 6 or 14. A quadric cone or a single point. Okay, let us go ahead. So, we covered what are the cases 1, 2, 3, 6 and 14. Other cases, let us say exactly one of A1, A2 or A3 equal to 0. Say, let us say A3 equal to 0. Then double star becomes A1 x square, A2 y square. Now, B3z will remain plus some c equal to 0, because B3 I cannot get rid of if F3 is 0, correct. Now, if B3 itself is non-zero, we make another translation, z prime equal to z plus c by B3, this is a translation. That will reduce this fellow to A1 x square plus A2 y square plus z equal to 0. This gives what? Let us go back. What it gives here? A1 square, A1 x square, A2 y square plus z equal to 0. So, this is either this case, that is elliptic paraboloid, or this case, hyperbolic paraboloid. So, 4 or 5 is covered. So, you get either 4 or 5. Now, if B 3 equal to 0, then this equation becomes A 1 x square plus A 2 y square plus C equal to 0. Now, C equal to 0, this gives which one according to our number? C equal to 0, C equal to 0 will give us 8 or 7 or 8, right. So, you have to turn your pages every time to go back to the equations. Now, suppose 2 of them are 0. If A 2 equal to 0 and A 3 equal to 0, you know the trick now. Then actually our equation becomes A 1 x square, B 2 will remain, B 3 will remain plus C equal to 0. Remember, whenever we have A 1, one of the A 1, A 2, A 3 non-zero, we can remove B 1, B corresponding B's. See, A 2 equal to 0, A 3 equal to 0, I cannot remove B 2 and B 3. So, B 2 and B 3 will remain. Now, if B 2 and B 3 both non-zero, then by rotation so that y axis becomes parallel to the vector 0 B 2 B 3, we get B 2 non-zero, B 3 and 0. Now, apply a translation and another translation along y axis to get C equal to 0. So, equation becomes A 1 x square plus y equal to 0. I have normalized it actually, not this, not same A 1, I have normalized it, maybe some other A, I mean some d x square plus y equal to 0. So, which gives case, which one? Let us go back, this one, right. So, this gives case 9. What was it, 9 or 11? 9. Now, if B 2, B 3 both 0, then in this equation B 2, B 3 is 0, C will be 0, A 1 is non-zero. So, C is 0. So, I get, so if C is 0, I get case 10 and C not equal to 0 gives case 11. See what is the equation? This equation becomes A 1 x square plus C equal to 0. So, C is 0, A 1 x square equal to 0. So, this is 11 and C equal to 0 just gives the plane x equal to 0. One more case left. What is that? A1 equal to A2 equal to A3 equal to 0. Then my equation is simply B1x plus B2y plus B3z plus C equal to 0. So, this is a plane. So, after rigid motion any plane is gives me of the form 10. Any plane is, we can assume after rigid motion is yz plane. This is yz plane, right. So, all the cases are covered. So, this is the proof for so called classification of quadratic surface. Quadratic surfaces are important because we know every regular surface locally, we have done this thing, done this exercise after doing principal normal so after doing principal curvatures. So, depending on principal curvatures K1 and K2, every surface locally looks like one of the quadratic surface, and I have only 14 possibilities of quadratic surfaces. So, any surface locally is one of these 14, any regular smooth surface is locally one of these 14. But when you patch together, then it may around one point it may look like a elliptic so it around one point it may look at ellipsoid, and another point it may look at as elliptic paraboloid or hyperboloid of one sheet or hyperboloid of two sheets, but locally they will one of them. So, that is the point. So, that completes the proof of this theorem, and that is the end for this lecture. The next lecture I will talk about, which I have not covered, something on surface area and equilateral maps.